I'm going to start the webinar. Okay, good morning, everyone. Welcome to today's webinar. My name is Kabir, and I'm with Bad Liver Research Group. I will be your host today. Today, we have Greg Patterson. He will be talking about post harvest soil testing. Before we dive in, I'd like to take a moment to thank all the counties that support and fund us. Because of them, we are able to organize webinars like these for you. A quick housekeeping items. If you have any questions during the presentation, please hold them until the very end. We will have 15 minutes for a Q&A session. However, if something urgent comes up or you need my help during the webinar, feel free to type it in the chat section. I will be keeping an eye on it throughout the session. Without further ado, let's begin today's webinar. And now please join me in welcoming our special guest speaker. Over to you, Greg.
Thank you, Kabir. Good morning, everyone. It's afternoon for me, but good morning for everyone out there. I'm going to try to go through some information on what is the correct way to soil sample and to get the right information, because there's a lot of people sampling out there that might not be collecting the information properly that can really skew your data and give you misleading information. So we're trying to clear up all that and talk about what is the most effective, most efficient way to take a sample. We first of all have to identify field variability. Look across this field here. You would think that this field was being windblown, but this is a hot, humid day. There's not a breeze blowing anywhere. Those leaves look like they've been blown over, but no, that's just stress in those areas and showing you the type of variability and different region has stress across that field. And I went out and tested that field, and where you see the lighter green, it's actually potassium deficiency in that soybean field. So we see this variability, we have to identify it, and we have to come up with what is the right way to do that. This is from a Timothy field in southern Alberta. Grower called me up and said he's had production problems, and I said, well, send me your samples and let's look at your sampling across that field. How have you sampled it? Have you sampled it in a grid or site specific? He said, no, you don't understand, Greg. Here we're flat land, it's all uniform. And I said, humor me. You would be surprised how much variability you have. So he went out and he site-specific sampled this in a 2.5 acre grid. But before he sampled, he told me he only had productivity in this field in one section of the field, that 1/4 section I've highlighted there. And you can see here from our general fertility index in our mapping system, it's the best part of the field, and there's a reason for that. So he sampled that. We looked at the types of soils he has in that field where he thought it was all one soil type. He goes from silts to loams to heavy clays across that field. So there's quite a bit of variability that will skew data. If you try to mix that all together, you're going to get an average of absolutely nothing, and it's going to give you poor information on how to deal with that. One of the biggest indicators we have in soil sampling that tells us about performance of the field is this K to magnesium ratio. And this is potash to magnesium in mill equivalents, not parts per million. So it takes into account soil type difference. And any time in a field you're above 0.15, your productivity is much greater. A lot of this field is below that. So when you just highlight some of the areas where he's close to 0.15 or lower, we have poor productivity. So I'm just kind of basically highlighting the areas that are the best. And you can see, again, that 1/4 section has the biggest majority of the stuff, the soils in the right range. The other thing he said, he had a lot of weed pressure. And the weeds were things like foxtail barley and fall panikin. But when you have soil types where your magnesium levels are this high, base saturation over 20%, things like sow thistle, fall panikin, and foxtail barley will become a real issue. And those seeds will stay in that soil for a long time. And the high magnesium soil actually helps germinate those seedlings because they like the anaerobic condition and those high magnesium situations. So we do identify with those, and it becomes a real issue. So another form of sampling other than bulk sampling is zone sampling. And a lot of people went to zone sampling again because they thought it was the best way to get a good understanding of variability, but cheaper than doing a grid sample. So we did zone sampling for a number of our clients because they wanted it done that way. We took images of the bare earth and crop to come up with those zones. But when we went across those zones and we sampled them, we actually found there was a lot more variability even within the zone than we could pick up from collecting those zones. And that's just looking down at a pail of cores that we've pulled, and you can see there's quite a variability in zones that are supposed to be all the same soil type. So zone sampling is also very difficult to get and understand real variability. Recently, there was a magazine come out, Soils and Crops, and they talked about soil sampling and the efficiencies of soil sampling and how many cores you need to take per sample. And in this document, and I sent this through to Kabir, it says that you need to take 8 to 20 cores per composite sample, not 1 or 2, but 8 to 20, and that will give you a good standard deviation of less than 2, which is what we consider decent information for pulling that together. So even though you're only taking it from a selected area, like we'll talk about site-specific sampling, you still need to take between 8 and 20 cores per sample to make up a good representative sample of that small sampling area. Another article I sent through was this one that was done looking at different grid size, because a lot of people try to, again, because of the economy of sampling, they try to reduce the number of samples of the grid size. So there's a lot of different grid sizes that are used out there that people work with to try to come up with a more efficient, more effective way to take samples. And a lot of times, sampling soils larger, grid sizes greater than 2 acres or 2 hectares is a common practice to reduce this number of samples. But this study evaluates that and shows that the different grid sizes on spatial variability of the information really have a problem with accuracy and cost of variable rate application of nutrients. So what this finding was that the total application costs for a 0.4 hectare grid size were lower or comparable to larger grid sizes, and give you a lot more information. So again, the overall consensus of this article says that you want to have a grid size less than 1 hectare in size to give you the most optimal, accurate understanding of that field for variable application of fertilizers, and really understanding the variability of that field. I sent out a piece of information in a newsletter just recently that talks about pulling samples and what you need to do. Again, in site-specific sampling, you want to select an area in the field. And again, I don't like to call it grid. I like to call it site-specific, because we do move the grid points around to match up topography or what we can identify as a management zone. And then we'll pull samples in a 15-foot radius, 15 to 20-foot radius, and sample those cores. And again, you're pulling 8 to 20 cores in that 15-foot radius. So why site-specific sample? I call it a soil audit. I need to know the variability. I may never sample that field that way again, but at least I have reference points I can go out and take that are based on the site-specific sampling we've done. And then we have the ability to produce a map for you that is color-coded and interprets what is going on based on the nutrient level or nutrient load. So you can have a better a picture of what's going on in the field, that you can then make some sense of what's going on in that. So we say, if we can't provide you with a map that looks like that field from the tractor seat, we did a poor job sampling. So that's what we start with. Now, site-specific sampling is not new. This actually started back in the 1930s, when fertilizer application was really just lime application. And this is a circular from the University of Illinois, and just how they dealt with variability and pH across the field for lime application. And farmers would go into the field and they pace the field off and select a number of sites. They would select so many paces. They go in and they select a number of samples for the topsoil. They take another sample site that would do topsoil and subsoil. So they walk across the field and do these different site locations and pull a sample to come up with information on just what is the variability in pH across that field. Then they would draw maps like this based on the information coming back, and they would go out and either off of back a wagon or buckboard or whatever it was, they would shovel the lime into those spots and then work it in. So again, site-specific sampling has been around a long time. We just have better tools to pull the samples with, to look at the information. We've got satellite imagery, and then we have very good variable rate technology to spread the fertilizer in the field or the lime in the field to get an accurate application. This is just a cost efficiency of a field where we we know we need to apply lime. This is a bulk sample of the field, looking pH of 5.7, buffer pH of 6.7. The overall lime recommendation in this field would be 2 tons of lime across that entire field. When we go in and site-specific sample that field, we see that the pH is not low in all areas, so it wouldn't require lime everywhere. And we do a look at calcium and base saturation of calcium, which we'll talk more about here a little bit later. But so we do understand that there's quite a bit of variability, and there's not the need for lime in all locations. And our real lime rec looks more like that diagram there. When you look at the economics on 156 acres, spreading 2 ton across that field, that's 314 tons. Site-specific sampling, the difference is 211 tons at approximately $35 per ton. That's a $7,400 savings across that field. So it more than pays for the site-specific sampling. And now you have good information on everything you need to do, but you've saved a substantial amount of money on just lime cost in this particular field. And that field is actually from the south of Brandon, but that's from Western Canada. The other thing we have to pay attention to when we're liming fields, particularly, is soil pH is low, and we go to lime, it's going to take about 4 or 5 years to get up to that 6.4 to 6.5, and it starts to level off. And then because of the parent material that's under that field, it will start dropping off again. And that's a period of a number of years that we go with poor yields. We have maybe a 4 or 5 year plateau where we get decent yields and it starts dropping off again. We oftentimes forget what we went through to bring that field up to better productivity. If you have to lime a field, and not everybody does, but if you have to apply lime to a field, you should have a maintenance program where you go into that field on a regular basis, maybe after harvest, and you broadcast apply a granular lime to that field to just continually maintain the pH. And that application might only be a couple hundred pounds of calcium or granulated lime material, but it allows you to avoid getting into large applications of lime and going through that large operation of liming the entire field. So what we need to do and what we're trying to do here is analyze our soil, get to know what we're dealing with in variability, and come up with a system that helps us understand why we have the reduced productivity in areas and how we can deal with it on a practical basis on application. If you're doing business with our laboratory, there's a lot of information on this report. It's not about the recommendation. We'll give you what we call a fertility guideline, but we like to put courses on and have my reps come out and talk to you and basically help you understand how to read this information so you can do a better job with fertilizing that field or managing that field based on the knowledge you're getting from this report, plus the knowledge you have on the farm yourself. Like I say, there's a lot of information here. We first of all do a cation exchange capacity on this field to give you understanding what soil type you're dealing with, and then we rate the nutrient status based on the soil types being what they are. So there's an optimal level of all these nutrients per soil type, and that's how we gauge what the level's at. That might sound pretty fundamental, but if you look at soil samples across the globe, and particularly North America, most laboratories, most institutions do not rate soils differently. They treat sands and clays differently, and I think anybody on this seminar will agree with me. Sands and clays are very different, and we need to look at managing them as with that difference in mind. You can just see here the difference we have here, and again, base saturation is a tool we put on there. We don't make recommendations based on that, but we put that on the report and teach our customers how to use that information to do a better job with fertility recommendations. The other thing on our report that's different than most people is this K to magnesium ratio I already talked about, and also a calcium to magnesium ratio that has a lot to do with the fundamental growth of the crop that you're trying to produce, and basically give you the right information on what materials you need to apply and how much of each material you need to apply. I wrote this article a few years back because there's a lot of people that were trying to, I don't want to say discredit what we were doing, but they really didn't understand base saturation, and they didn't understand why we rated soils the way we did. All the information we deal with globally comes from work that was done back in the 40s, where they looked at calibration work on soils and come up with what is the optimum level of a nutrient in the soil. So the one approach was a sufficient level approach where they applied nutrients to a field until they didn't have any further response. And that's what they established as a sufficient level of available nutrients for that nutrient. At the same time, there was a group of researchers doing work where they looked more at the base saturation cation exchange ratio concept. And then again, by applying fertilizer to a soil, they established where the optimum level was on a relationship between these cations. And both are very real concepts, but both have merits and they should be used together. It wasn't until 1975 that Fisher said, well, we're not looking at this practically. We're not dealing with this information cataloging soils based on sands and clay. So Fisher used cation exchange capacity to take this information and catalog the soils based on if they're sand or clay and establish what the ideal optimum nutrient level would be in a sand versus a clay. And unfortunately, even today, a lot of people do not do this. They still use the Slane approach or the base saturation approach, which together they work really well, but independently they can cause some misgivings. So as I said here, this is just a simple chart. This comes from Fisher's information. The 0 to 6 are sands, 7 to 15s are your sandy silt loams, your 16 to 25 is your clay loams, and then 25 plus, obviously, the heavier clays. Most information you get from fertility handbooks deals with soils all being a clay loam. That's 16 to 25 CEC, which you can see here by the numbers that Fisher sorted out here is not the optimum range for all soil types. So first of all, we have to establish what is the optimum level for that field. And that's where site-specific sampling comes into play. This is the base saturation of those soils as well. And when you look at base saturation, there's a lot of people that don't believe in it. Base saturation is just a simple way of exhibiting the coefficient of diffusion of these different soils for the cations. In other words, how readily available the nutrient is or how easily that soil type will give up that particular nutrient into soil solution and available to the crop. And I have people, the reason I wrote this article, I have people that don't believe in base saturation or this concept. I also have a degree in animal science, and one of the magazines or reference text I used back in college was Hoard's Dairyman. And this is actually out of Hoard's Dairyman going back to, well, I'll date myself a little bit here, but the mid 70s. And in that book, it says if you have a equation like this where milliequivalents of potash divided by milliequivalents of calcium and magnesium, and that number is greater than 0.07, you will actually be producing a forage that could cause milk fever or grass tetany. So if that can be predicted from looking at these soil types and looking at these base saturation equivalents and be dictated right through to the forage the animal consumes, there's got to be something real here. And that has not changed today. We use this all the time when we talk to dairy growers or beef growers where they're having problems with livestock. And this is a real phenomenon. And it's not about potassium being too high. It's about the imbalance of the K to mag and usually a low level of available calcium. So we need to pay attention to this. And we need to pay attention to what is the optimum level in these soil types. And clays, the higher CECs are much different than the sands. We need to treat them that way. And really, when you look at the differences here, if I have a sand, our potash at 120 ppm would give me 6%, which would be a perfect range. But to get into ideal range in the heavier clays with CECs 20 plus, I have to be 250 or greater in potassium to be in that range. So we really have to understand what are these optimum levels, and we need to be able to soil sample and build this audit, as I said before, in understanding this information. When we look at the base saturation concept and we look at the coefficient of diffusion, if we have good soil moisture, 3% saturation in a sandy loam would do an excellent job. But if we have poor moisture, we likely have to be up closer to 5% saturation to get the available potash into soil solution. And again, crop demand also plays a role in this case as well. So if you understand this and you understand when you're putting your fertility programs together and trying to manage a field, that base saturation information is on the report so that you can understand what is the predictable availability of those cations. We also provide our TerraSite maps to you that are color-coded, very intuitive mapping software that helps you understand from a picture format what is going on in that field. And those TerraSite maps basically show you where the levels are. This happens to be from the Discovery Farm in Saskatchewan. We sampled it. And if you look at the pH of that farm, and most people looking at that would say this farm does not need to be limed. However, when you compare that to available calcium, you can see a large portion of that field is calcium deficient and actually would benefit from an application of lime. And this is something that's a real problem in lots of areas in Western Canada, is that we focus too much on pH and we don't understand what's happening in these fields, and it's causing us all kinds of problems without this type of interpretation. What's happening here is the magnesium is so high in those areas, it's reducing the availability of potassium because it's competing with it. And even though my pH is where it should be, it's not because of calcium, it's because of magnesium. Another thing people don't understand, that magnesium keeps your pH higher or elevates it more than calcium does by 1.5 times. So high magnesium gives you a false reading on available calcium, which is causing us all kinds of problems. Magnesium over 20% saturation tightens up your field, makes it anaerobic, just generally poor health. So when we look at the relationship here, we've got a lot of that field that is in need of calcium. It should be something we consider when we're liming or trying to deal with this. It's not just about pH. This is an example of that. This is not from Western Canada, but an example of a soil report that has decent pHs for the most part. And that one at 7.2 pH has 22% saturation of magnesium and 63% saturation of calcium. This area of this field could actually benefit from 2 tons of calcitic lime. And those are things we need to keep in mind when we start looking at some of this information. And again, just looking at neutralizing value of calcium and magnesium. And this is right out of an old text that I actually used when I was in university, Buckman and Brady. It just shows you the neutralizing value or buffering capacity of magnesium oxide versus calcium oxide, and just basically what I'm talking about in this information. So we need to understand how to read this report. We need to understand what these numbers mean and understand as you walk across a field. And the best way to do that is site-specific sampling and be able to look at the different zones based on the production of that field and be able to basically make some real solid decisions on how we can improve the overall productivity of these fields. And again, that K to magnesium ratio greater than 0.15 is something we need to achieve. We get over 0.35 and we have a magnesium problem, whereas under 0.15 it's a potassium problem. And both potash and magnesium together drive energy in the plant, and it's something that we need to keep in mind. The calcium magnesium ratio, again, in most of your soils will be 5:1. And again, it's just basically these ratios give us information at a quick glance on how are we going to treat that area. Is it K-Mag we have to use? Is it muriate we have to use? Is it calcitic lime or dolomitic lime we have to use? It just helps us in determining what type of product we need to look for. So again, that Discovery Farm, when we look at pH and buffer pH, it's not really calling for lime in most of the field, but even in the lower end of that field, the buffer pH is lower and we would ask for lime. But I would do my lime prescription here based on percent saturation of calcium, because there's a lot of things going on in this field where it is located that is completely calcium related. So look at magnesium levels in fields. Again, we want to be between 10 and 20%. Below 10, you have energy issues. You need to add magnesium to it. Above 20, it's becoming tight and anaerobic, and again, interfering with both potassium and calcium availability in those fields. So it's something we can manage, but we need to understand what it is. So the ideal level is less than 20%, but in some of your heavier clay soils in Western Canada, that'll start someplace between 16 and 18%. So again, these are just ballpark information, and all soils are different, and we need to understand how that difference plays a role in our own production system. Why do we worry about this? Well, what are some of the biggest issues you have in Western Canada? Thistle, kochia, clubroot, Aphanomyces. These weeds and these diseases use oxalic acid as a mechanism to, to survive and penetrate the plant. Kochia secretes oxalic acid to basically, as an allelopathic effect, to compete with weeds in this area so it can dominate the area. Calcium sequesters oxalic acid and neutralizes all these things. So if you have kochia, if you have clubroot, if you have Aphanomyces, if you have thistle, you likely have excessive magnesium and low available calcium. So whenever you see diseases or you see weed pressures or even insect pressures, look to those as something that is really demonstrating the spatial variability with your field, and look to what the cause is, not just what the treatment should be. Look at what the cause is so that we can do a better job controlling some of these things. Obviously, it's not going to control 100%, but you're not going to get any control if you don't start addressing some of the reasons for it. So again, magnesium is a problem with weed pressure. We outlined that before. It's also a problem with a lot of those diseases we talked about. So things like clubroot, Aphanomyces, Scarlatina as well. And on the other side, on the left-hand side, you can see the different diseases or weeds pressures that are also associated to calcium deficient soils. This is a trial we're doing in the lab right now with a particular field in Alberta that wants to increase his canola production, but he's having problems with clubroot. He sent us 3 soils in to look at, and 2 of the soils are growing canola now and have clubroot issues. The one he wants to start growing canola in, and he sent the soils in. We have good spore count, high spore counts in first one and the second one. The third one we have virtually no problems with. But if you look at the base saturation of calcium in that field, it's at almost 85%, where the other ones are at 53 and 50% saturation of calcium. To control clubroot, forget about pH. You need to get your base saturation of calcium north of 67% saturation, and you'll have better success in controlling clubroot. That's just the soils, looking at them, the 3 different soils. They don't look all that different, but there's a big difference in the mineralogy of those soils. That's just the trial itself, looking at clubroot and clubroot control in a trial that we've put together. And again, infested soil with a formulation that we've put together, plus one of our biologicals. And you can see the top one here, how good it looks. The second one here, again, with another formulation, and we're using calcium nitrate as well here. Probably calcium nitrate doesn't last long enough. We need different forms of calcium to do that. And then to control the infested soil and control, you can see the difference in growth in that canola. And that's at 44 days after planting. So we've done a lot of work on clubroot and canola, and we're still struggling to come up with the ideal method of applying what we need, both in a biological control, plus how we handle calciums and nutrients to make sure we get it in the right position. Because we think we know the answers, but then we have to take it to the field and get it done. So with our soil testing system, we have these maps that we put together. We like to map it out in this color-coded maps. The picture's worth 1,000 words. And this really helps you as a grower to look at your field and identify with those spots to see, this is what's going on in your field. We look at this particular slide set of potassium. The top left-hand corner is cation exchange capacity of the field, so it's showing you the soil in this field goes from a sand to a heavy clay. So again, lots of variability. The top right-hand side is parts per million. The bottom left-hand is base saturation. And the problem with those 3 is they're all 2-dimensional. So the bottom right-hand corner is an index value, which takes that information and brings it to more of a 3-dimensional look at available potassium in that field. And that's what we try to do, is extrapolate the information in enough ways so that it does look like the field from the tractor seat, and we do understand how we can deal with those variabilities. So again, site-specific precision sampling program allows these detailed maps, and also gives you information for variable rate application of fertilizers across that field. Just looking at this demo field, this shows you again a series of maps and how each nutrient here has a different color code based on its optimum levels. So obviously some variability and differences across that field. We're now working with, in our mapping software, we give you lime prescription maps, potash prescription maps, phosphorus, sulfur, a number of different maps so that you can actually go out and variable rate apply these nutrients if you wish. This is looking at our general fertility map and with our soil health index. When you compare these maps and start looking at the relationships and overall general fertility, you can see in the general fertility map, there's some correlation to the overall general fertility and what we classify as the soil health problems. So again, the red zones, the yellow zones are low soil health. The green zones and light greens are the higher soil health areas. When you look at all the maps and start comparing, this soil health index has a real strong correlation in this case to potassium as well. But also we look at magnesium as a bit of a correlation. So there's a bunch of influencers in our soils that have a real strong influence on the microbial populations that we classify in our soil health testing. So when we look at this, another way we interpret information, we look at the chemistry, the biology, the mineralogy. When we're looking at healthy soil and fertile soil to come up with how are we getting our soils into a more healthy position. And then we have now this soil health test that you can ask us to run for you, which is actually a complete test. But we have parameters on here that give you guidance on the direction to go to make this field a healthier field. We want soil health indexes over 40, and that soil health index is in the bar chart on the bottom right-hand corner. When you look at that, and I look at this report, we put information here where the optimal level should be for certain nutrients that we know directly impact soil health and soil microbes in the rhizosphere. And if one of those are out of range, you need to work at getting those into range. We also give you another set of parameters on phosphorus, on pH, on aluminum, and information on potential mineralizable nitrogen to give you good information on how that field is performing. And then your CO2 respiration and your reactive carbon, all this information helps you identify with what is the missing piece to give you that healthier soil that helps you produce a better crop. We also know once we get over a soil health index of over 40, disease pressure is going to go down. We're going to have nitrogen fixation is going to be happening greater in that field. The biology is going to be releasing nitrogen from the organic matter from the soil itself. And again, some of these organisms will penetrate the plant and actually fix nitrogen. So we know that the efficiencies change immensely as we push that soil health index up over 40. And this is just some research data where we looked at the different colony counts based on things like potassium, general fertility, boron, calcium, phosphorus, on a number of different organisms in fields, so that we actually do know how we can manipulate those and how we can improve what we call the indicator species in the rhizosphere that give us that healthy soil type. The other thing I'd like to talk about before we finish today is talk a little bit about nitrate testing. It's big, it's something you guys do a lot in the West, but I don't think people realize how much variability and available nitrates across that field there is. We oftentimes get people taking a bulk sample to do a nitrate test or a single sample across one field to do a nitrate test. And if you're not in the same spot year over year, it's really hard to predict or understand what's going on in your field, because you can see the variability this year in this test on nitrates across that field. And if I was in one spot where the nitrate was high this year, and I went back to a different spot in the field next year, and it comes in low, it might not be because of what was residual from my cropping system. It might be just that soil type is definitely lower in nitrates overall. And it has a lot to do with soil type, organic matter, water holding capacity, that all influence potential mineralizable nitrogen. But there's more things than that. It's the amount of rainfall we had that year, the temperature, a whole bunch of things that influence soil nitrate levels. The point here is one size does not fit all. We need to have a better understanding of what is the variability so we can make logical decisions on that field and remove a lot of the guesswork. And a lot of that is something we deal with every year. We growers are calling and said, that's not what I expected from nitrates. And we rerun the sample, we get the same number. And they still don't believe it, because that's not what they got last year, or not what they expected based on the crop they pulled off, or based on the amount of nitrogen they used. So we need to understand there's a lot of influence there. And we first of all have to understand that it could be weather, it could be rainfall, it could be crop load, but it also is variability across the field. We need to make sure we reduce that or eliminate that as a factor so we can make a better judgment call on what we're actually going to apply. Um, when you have overall lower general fertility, your nitrogen use efficiency goes up with better fertility, so you don't need as much nitrogen in a spot if your GFI is higher. If your GFI is lower, you need to put more nitrogen on to get the same results or even grow the crop. So again, the better the overall fertility, the better the soil health, the more nitrogen use efficient we'll be in our production system. And again, looking at some of the things that have a play, a nitrate availability, organic matter, and cation exchange capacity both together, we use to predict potential mineralizable nitrogen. And it plays a major role in how much of this nitrogen is going to be released over the growing season to the growing crop. And regardless of moisture, I mean, it's inherent to soil properties and soil types. This is just a map of the research work that was done on that estimated nitrogen release by soil type and organic matter. And it's different in zones. And you can see by this map, there's about 5 different zones. And the reason for the difference in the zones is obviously, if you're in a colder climate, you're not going to get the mineralization you're going to get in a warmer climate. So we have to make an adjustment in our prediction for potential mineralizable nitrogen based on the growing season and the length of season that these organisms have to work on the organic matter to release the nitrogen to the crop that you're growing. And that's just another chart. It's a text sheet we have to just, goes through that you can download from a computer system to show just in your soil type based on CEC and organic matter what you could anticipate as a nitrogen release in that soil type. The other thing we found that was really interesting lately, and that's that other nutrients play a role in nitrogen release. And again, we did this and started gathering this data because of all the interest and all the issues we have on variability of nitrates, not just soil type, but we're looking at here the available phosphorus in the soil, and we're looking at our phosphate saturation here to understand that. The more available phosphorus we have in the soil, the more nitrates we'll find. So your nitrogen release, your organisms that are breaking down nitrogen and making it available to crop, increases over soil type and over phosphate loads. We're doing this with all the elements. We're looking at potash, we're looking at K to magnesium ratio, we're looking at the micronutrients. They all are looking like they're having a significant impact on nitrogen release from those soils. So there's a lot more to it. There's a lot more information we're trying to put together to get some common sense out of this. But the most important thing is we need to do a better job of getting an understanding of the variability of these fields so that we can take into account the overall variability of the field as part of that, particularly in this case, of nitrates. So in conclusion, we need to do a better job of soil sampling. Before we start, we need to, what are the variable factors of the system we're trying to measure? We need to identify what the possible causes could be, and then what changes can be made to manage some of that variability. So the first place is how big is the grid size? I don't like to just lay a grid. I call it site specific because you're going to move those grid points around. But you want to establish a sampling point from that one article showed you of about a sample every 2.5 acres or every hectare. And that shows us the most efficient way of determining that variability. But you also need to use things like drone images or satellite images or combine information to pick out where those production zones may be so that you can lay the grid points in a zone that's going to give you the information you're looking for. So we will move those around. That's why we call it site-specific sampling and not grid sampling. We need to do a better job of identifying the variability and then pulling samples to give us the information to take that to make management decisions on. So with that, I hope we're in good time here for questions.
Okay, can you hear me?
Yeah.
Perfect. Thank you so much for an awesome presentation. Now we'll open the floor for Q&A. If you have any questions, you can type it in the chat section or Q&A, or if there's someone who doesn't like typing, they can raise their hand and I can allow them to talk. Is there anything else you want to add on to the presentation by the time people are typing?
The only thing I want to add is I have representatives all across Canada, like Norm's on the call here, that you can call or ask. We do have um, companies we work with and independents that do custom soil sampling for us that we can put you in touch with if you can't pull the samples yourself. Or, simply you can call us and ask us what you need to do your own sampling. The key here is to be able to understand what is this, what are you going to use to actually identify those zones? If you lay the grid and start moving the sample points around, how do you identify those zones? So that's the most difficult thing in this whole process.
Perfect. There's a question for you.
Yeah.
Just wondering about soil moisture impacts on measures of soil health. How do you address this?
Soil moisture has a big impact on soil health because when we get low levels of moisture, our microbial activity actually stops. So if you're using something like CO2 respiration to measure that, you're going to see low respiration in those drier soils, and it will reflect in our soil health index. And we do take that into account when we do the sampling. So if you did a soil health test with us and it came back on the low side, and your CO2 respiration was also low, but all those other minerals are in line, we can look at that data and say it's a moisture-related problem because your nutrients are where they should be. So we can actually identify when it's a moisture-related problem. But that's not as big as an issue as you think. These microbes don't disappear. We can still find them. They just might not be as active or um, as many, I guess, plate count, if you will, in some of the drier soils. I hope that made
Perfect.
sense, but it does have an impact.
Perfect. Hopefully that answers your question. We have another question. How is the best way to set zones?
How's the best way to set zones?
Yeah,
Um, well, first of all, I said I don't really like a zone sample, but if you mean a site-specific zone, I use satellite image. If we're doing sampling for you, we'll go out and take a satellite image and then try to lay the grid based on what the satellite shows us in biomass. Obviously, trying to target low biomass and high biomass so we can see the variability difference. If you have a yield monitor from a combine, it can give us the same information. So there's a number of ways we can actually figure that out. If you have a really good trained agronomist pulling samples, they can usually get a pretty good idea looking at the field just where those zones should be, those sites should be. So there's a number of different ways that you can pick out that information.
perfect. There's another question. Can a yield map help?
A yield map?
Yeah,
Absolutely. Yield map off our combine is a great thing to actually lay your zones out. Let's say you lay a grid across the field every 2.5 acres, just straight line grid. Then you lay your yield map over that, and then you move your sites in that grid to match the yield map. So you'll see production zones that vary across that field. You just move your points that you're going to sample in, and mark your point based on what you see as production zones coming off that yield map. We oftentimes use yield maps.
perfect. Hopefully that answers your question. Okay, there's another one. Are the very high local variability in measure values like the K slash mg values shown on your example field map due to mainly to test sample variability effect or actual soil composition and or history effect? Perhaps things like topography, historic organic matter, water flow, and water table effects.
All of that. When we talk about high mag soils, it's inherent in the soil type you're dealing with. You'll never get rid of it. It's there. It's not because you did something or applied something to cause the high mag soil, because it doesn't build that way. It's from the natural parent material. Understanding where that break point is, understanding where the base saturation is, and being able to identify that allows you to put correctives in place so you can manage it. And again, with high mag over 20%, the corrective is apply more calcium. And it works quite quickly. I mean, gypsums are faster than calcitic limes, but limes last longer. So because the economics, oftentimes we go to a lime material rather than a gypsum. So yeah, you're not going to do anything about changing that magnesium level long term. It's going to come back because it's part of the parent material. But at least understanding with a map that we produce for you and there's high mag soils, you know what you have to deal with and how to manage them. You don't want to go lime a whole field because you think you have high mag, because it might be, as I showed you in some of those maps, it might only be a portion. So you want to be able to use variable rate to deal with that. Or you're going to end up putting calcium where you don't need it and not enough where you do need it.
Perfect.
I hope that
Hopefully that
answered the
answers your
question.
question. Yeah. Okay, is there anything else you want to add on by the time anybody else wants to type the question?
The reason I spent so much time today talking about that calcium magnesium relationship is particularly in the Alberta area, we have a lot of it. There's a lot of high mag soils, and it's causing us a lot of problem, particularly with clubroot. People try to attribute clubroot to pH, and when you have high pH, it kind of goes against what the common doctrine is about clubroot. I got high pH, I still have clubroot. Why? It doesn't make sense. Well, it's what I tried to show you there. Magnesium elevates your pH more than calcium does, and we still have to lime those high pH areas. A lot of people say, I don't want to lime those high pH areas because I don't want my pH any higher. You lime a high magnesium soil, your pH will come down. Again, magnesium holds your pH up 1.5 times more than calcium does. So as I start removing the magnesium from the soil particle, I will replace that with calcium, my pH will come down. So I'm not afraid of increasing pH with an application of lime when I'm trying to get rid of magnesium.
Webinar.
We type in questions or we just, did I lose you? Hello?
Hello, can you hear me?
Yeah, did I lose you?
Yeah, I think so. Yeah, I guess there's no more questions.
Okay.
Yeah, I guess we can conclude the webinar now.
Yeah, it's
Thank you,
saying
Greg, for yeah,
saying our
yeah.
connection
Thank
is
you, Greg.
unstable.
Yeah, yeah, it happens sometimes.
Yeah.
Okay, thank you, Greg, for this excellent presentation. It was truly a pleasure to have you with us today. That brings an end of our webinar. Thank you all for attending. We hope you found this webinar informative and useful and enjoyed the discussion. If you have any feedback or suggestion or for future topics, feel free to share with us via email. Have a great day, and we look forward to seeing you at our future events.
Like I said,
Thank
if you
you.
have any questions, any follow-up questions, just get them to us and we'll send answers.
Perfect.
Okay?
Sounds
Yep.
good. Thanks, guys.
Perfect. Have
Thank
a good
you.
day. Thank you.
Yep.
Yeah.
Bye.